Hello everyone, my name is Dan Ping He from Beijing Jiao Tong University. I'm going to make a tutorial on ray tracing simulator. These are the contents. First, I'm going to introduce how to install the RT simulator and its architecture, and then a simulation example will be provided on how to create projects and how to configure snapshots. First of all, unzip this file, which contains all the documents and the codes to run the simulation. In the database folder, we have antenna, material, scatterers, scenario libraries. For each libraries, we use JSON format to describe the models, which will be later used by the ray tracer. The help folder contains a small tool to help you check whether the configuration of the antenna rotation is correct or not. It is especially useful when the antenna is directional antenna or when you use beamforming technology. The kernel folder contains the RT executable file, which is the executable of the ray tracer engine. The project folder is where you can put your simulation task. The tools folder contains all the tools and functions in order to convert the files into the JSON format or to configure the antennas, the scenarios, and so on. It also contains several documents to help you understand better how to use the functions, the models. Then I'm going to show you how to trigger a RT simulation, how to create a simulation project, and configure a snapshot. In the project folder, we provide you a simulation example. There are 3 MATLAB scripts. It's simulation by code, simulation by GUI, snapshot configuration script. And we can open it by using MATLAB. Before we trigger a simulation, we should first configure the path of the MATLAB. We choose this include or add the folder, includes the subfolders, and then we select MATRT tools folder and save it. We first have a look into the snapconfigure.m. It's a function that helps you configure the snapshots of a simulation task. First, we can set the TX and RX positions. In this example, the receiver moves along y-axis from 1 meter to 50 meters, and the step is 1 meter. The transmitter is static. The set position function is to set transmission and receiver position. The first 3 parameters defines the locations. The last 2 parameters defines the locations in azimuth and elevation angles, respectively. Then we can configure the antennas and the transmission power. Here we use omnivertical polarization antennas for both the receiver and the transmitter, and the transmission power is set to be 25 dBm. One of the most important features of this ray tracer engine is that it can support mobile scatterers inside the scenario. It is very important, especially for the 5G mobile networks. For example, the V2V or high-speed railway communications, where there will be or might be mobile scatterers around TX or RX. And therefore, this section will assist you to configure the mobile scatterers. This line will load the JSON file from the scatterer database. And in this example, we have two scatterers of the same model, but they are moving with different speed in different directions. And then we add the scatterer into the snapshot by indicating the original position of each mobile scatterers. And finally, we save the snapshot into this file. There are two methods to run the simulation. First is by MATLAB code. The second is by GUI. First, I'm going to introduce simulation by code. As you can see that there are clearly marked with 7 steps. The first is to define where the scenario model locates. Here in this example, we use the scenario model in the database. And then we create a snapshot by running the snap configure script. Then we configure the simulation task. It's the main part of configure the simulation. We first initialize the task class and determine the scenario file and snapshot file according to the first and the second steps. Then we indicate where is the material file. As we introduced before, in the database there is a material library, and in this case we use indoor material JSON. The material library indicates not only the material type but also the dielectric parameters, the scattering coefficients and transmission coefficients, and so on, that are needed to compute the propagation mechanisms. And then we specified where is the output file. Here in this example, we save the results in the result folder. Then we set the frequency. The first variable is the center frequency, the second is the bandwidth, the third is the frequency step. Afterwards, we are going to configure the propagation mechanisms. In this RT, we have direction path, reflections, scattering, diffraction, and transmission. 1 indicates that this mechanism is considered in the computation. 0 indicates that we don't need to compute this propagation mechanism. Afterwards, we save the task file into folder task with the name task.json. And in the fourth step, we called RT engine. The call RT function has 3 inputs. The first is the location of the task file. The second is the starting snapshot. The third is the number of the snapshot we want to simulate. The 5th, 6th, and the 7th step are the process of the simulation results. The 5th step will load the results according to the output directory specified in the task configuration. The 6th will record a video demo for the simulation results. The 7th step is to export rates, which we can check through SketchUp. So in this example, we observe the direct path, reflection path, diffraction, and transmission path. The scattering is set to 0 without observation. After we finish configuring the simulation task, we can run this script, and the figure 1 is popped up. The red color indicates the transmitter, the blue colors are the receivers. There are 50 receivers. And in the common window, there is a progress of the simulation. After the simulation is finished, the demo is recorded to a video, and this is the figure 2 shown in the MATLAB. As you can see in this left figure, different type of rays absorbed as the ray tracer can be used to trace all the rays. The blue lines is the reflection, the orange is the diffraction, the red line is the direct path. Two scatterers are moving along different directions with different speeds. Afterwards, in the seventh step, the rays are exported to JSON format. Just save it. Then we finish all the simulation, and in the folder we have a video recorded, which is the same demo as we see in the MATLAB figure 2. There's one thing that we should pay attention to in the task file. If we have a look into the scenario, material, and the output directories, the simulation bytecode will configure it to absolute directories. It's not easy to use if we want to distribute or copy it to another person or to another PC. We need to reconfigure the simulation task. So best way is to configure the directory into the relative directories. By using the GUI, we can solve this problem. The GUI can be launched by using UIRT command. If we open it in the current simulation project, it will automatically load the task.json file in the task folder. In the left part of the panel, we have the project files indicating the scenario, material, snapshot, antenna, and the directories of the files. We have all the simulation configurations, including the propagation mechanism, the transmission power, and the frequencies. We can configure the scenario here. We use empty indoor and indoor material. For the antenna, we use omni vertical polarization. Then we save the simulation task, and here is the indication of the status. Then we close the GUI and reopen it. And we can find that all the directories are converted to the relative directories. Here again, we can have the preview of the snapshots. The red is the transmitter, the blues are the receivers. Then we can start the simulation. And here it allows to configure the starting point and the finish point of the snapshots. Again, we have the progress of the simulation. After the simulation is finished, this button, the status will be changed to restart simulation. And we can view the simulation results afterward. Which is the same as the video record in the simulation bytecode. And right now I'm going to teach you how to configure a simulation project in a fast way. Type UIRT in the command window. Then it will ask you to select a project directory. You can create a new folder called test. And now we have all the fields are blank. But if we look into the project folder, all the subfolders are created automatically, but inside each folder they are empty. And inside this test project, we call UIRT. And select test. The same as the previous example, we just specified the scenario, the material, the snapshot. So in this project, there's no snapshot, but we can use the previous one. The antenna, we also choose vertical polarization. Transmission power, we can set to 15 dBm. And if we look at only up to first order reflections, diffraction, transmission. So we don't observe scattering and the diffraction paths. We only observe the first order reflections. And the frequency will be 3 GHz. The bandwidth is 10 MHz. We can choose to modify it to 100 MHz. And okay, then we save the configuration. Then it indicates that the configuration is saved. And we can start simulation. So all the progress is finished and the status is changed. Then we can view the simulation results. Then I'm going to teach you how to convert a SketchUp environment model into JSON format that can be used for the RT simulation. Inside the database folder, under scenario subfolder, we have indoor SketchUp model as an example. Then we open it in the SketchUp and we can see this scenario. It's just an indoor environment. And if we unhide all the faces, we have this complete model. We export to 3D model and save type as Collada file to any place that you want to save. For example, in the database, pay attention to the DAE export options. We only choose these two. The third one is to save all the faces into triangles. The last one is to keep all the components. Then we just export. And in the scenario folder, we have indoor DAE. In the command window, we just run DAE to JSON. It's in the tools folder. Then we select the Collada file as indicated here. It's in the database scenario indoor. And we will link the material libraries. Here we choose the material list instead of the detailed material parameters. So we use material overview and open it. And as you can see, the scenario is true as an apple. And then the program asks you to select the scenario file to save. For example, we save it as in empty indoor version 2. Then it's saved. If we want to use it for the simulation, as we did before, UIRT. Yeah, we choose this folder. The scenario here we choose empty indoor version 2 and save configuration. And start simulation again. Okay, it's finished. So here we finish our tutorial. Thanks for your attention. For any questions, you can contact me. Thank you.